Okay, so we're going to start with just a definition of continuity, all right? A function is continuous if. All right, now we're going to get away from the non-calculus definition, which is drawing it without picking your pencil up. Okay? So I am going to draw a picture of what continuous looks like. Okay? Continuous. You can draw it without lifting your pencil. However, that is not specific enough for us anymore. So this is the limit as x approaches a from the left. All right. This part right here is approaching from the left. How do I say with limit notation that something is continuous? The limit from the left is actually the same as the limit from the right. Yes, one more statement though, okay? Because basically I'm trying to say, how can I draw a graph without lifting my pencil? Well, you trace it from the left and the right, and the final step is the point, right? All three of those things have to be equal. That is really the definition of continuity, okay? Drawing it without lifting your pencil means that the left side and the right side are all in the same place as the point. Okay, so now we're going to do a couple more vocab words. We're going to talk about discontinuities. And then we'll use the definitions. Discontinuities. We have the first one, which is called point or removable. And we're going to look at this definition in terms of this type of discontinuity. So I'm going to draw what this looks like. Okay, this is what a point or removable discontinuity looks like. Now, so I don't have to rewrite a ton of things here. 1, 2, 3. We have 3 statements up there. I'm just going to write down the numbers here. So the left limit is actually equal to the right limit, but it's not equal to the third statement. See that? 1, 2, 3. For this particular picture, the left is equal to the right, but not equal to the point. Okay. The second type of discontinuity is a jump. Okay, so I'm just going to draw what a jump looks like. And I'm using the picture to help me understand what's happening with the limit statements. So the left side, the right side. Okay, so 1 does not equal 2. The left and the right are not the same. All right, this is from up here. The left and the right are not the same. Now, it's equal or not equal to 3. It doesn't actually matter what happens with that last part because it already failed. You kind of check them in order. Does the left equal the right and equal the point? infinite or non-removable. Okay. This infinite discontinuity that we're talking about is actually referencing a vertical asymptote. And so, dot, 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 I'm just going to draw. Okay, it's possible that they're pointing in the same direction. It's also possible that they point in opposite directions. But that's still a vertical asymptote that we're looking at. Okay. So I'm going to think about my steps here. The left limit and the right limit. So here, the limits are the same, right? Because they're both pointing to positive infinity, okay? But they're equal to positive infinity. Now 3. Okay, statement 3. That's the one about the point. Is there a point here? No. So it is undefined. Okay, undefined. Just give myself a little more space. Okay, so 1 equals 2 equals positive infinity. Okay, so what about this next statement? 1 doesn't equal 2, but they're still infinity. Okay, so it's still infinity. Is there a point? Nope. 3 is undefined. So as I'm looking at the infinite and the non-removable discontinuity, there's one thing in particular that you have to look at. Notice here that the first 2 limit statements are not equal, but it matters how they aren't equal. Okay, so the infinite comes because, right, the limit was equal to infinity. That's what makes it an infinite discontinuity. It's because you ended up with a vertical asymptote. All right, 4 vocab words. Continuous, point or removable, jump, infinite or non-removable. So we're going to draw a picture, and then we're going to write the statements and label it with words that describe it. All right. Ready? Okay. All right, graphically. Okay, you don't need a grid for this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. Don't draw it too small. Just going to draw it in sections. So you've got a point here at 1, 3. You have a point, open point here at 2, 1. Okay, so now I've got 2, 3. Okay, so 2, 3, and 4, 3. Just a little frowny face. Okay, and dot, 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 dot. We'll draw an asymptote here, and we'll just curve it up.
That close that up too.
Say that again.
Is that closed out over 2?
Yes, yes, it is. Let's say all the points are supposed to be at integer coordinates, whatever closest integer I got them to. Yeah. Yeah. Okay, so here is, okay, is the graph continuous? Continuous. Okay. Right, so is the graph continuous? Describe using limits and words. So we're going to look at a couple different x coordinates here. All right, the first one, x equals 1. Okay, so is the graph continuous at this point here? Okay, so left, right, point. Okay, yes. Okay, yes, it's continuous. Continuous because, right? Describe using limits and words. Okay, the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right equals f of 1. That is the reason it's continuous, because I trace it from the left and I trace it from the right, and the point is all in the same place. All right, so I'm going to evaluate it so you can see this. So the limit from the left is 3. The limit from the right is 3. And the point is 3. See that? They're all the same. That is continuity. All 3 of them equal. Okay. X equals 2. Same format. Is it continuous? And why? Okay, random name calling. You have a lifeline. If I call your name, you can ask a neighbor for help before you answer, if you would like. Daniel, is it continuous at x equals 2?
No, because of the thumbs.
Okay, awesome. No, we'll say not continuous because, all right, I like the vocab word there, because there's a jump. But now we have to write the limit statement that goes with it. Okay, next. Ben, is he still gone? You, Ben? Or yeah, you're okay. He's all right. Olivia. Where are you? There you are. Okay, what is the limit as x approaches 2 from the left? 1. Okay. Pedro, what is the limit as x approaches 2 from the right? Okay. Yep. See that? Not equal to. Okay. Next one. Kara, what is f of 2 equal to? The closed point is at 3. Yes. Right? This is actually the point on the graph. The left, the right, and the point. Okay. So right here, see this? The left and the right aren't equal, so that makes it a jump. All right, x equals 4. Okay, let's follow the format. Aaron, is the graph continuous at x equals 4? Wait. At x equals 4, which is right here, is the graph continuous? No. Okay, no, it's not continuous because. All right, Colin. Because why? Give me the word. Hold on, at x equals 4. What's the word that goes with it? Okay, because this one is a point discontinuity, or we sometimes, you might see that word, removable. Okay, limit statements. You're not here today. Aaron, what is the limit as x approaches 4 from the left? It's actually 3.
Oh, but yeah, it's 3.
Yeah. Okay. I know. Here. See if we can see a little bit of the picture at the same time. Okay. Here we go. So the limit as x approaches 4 from the right. Dylan, what is the limit as x approaches 4 from the right? 3. Okay. And Caroline, what is f of 4? Yeah, it's undefined. There's nothing there, so it's undefined. Okay, notice the left and the right are the same, but the point is undefined. It's missing a point. It's a point discontinuity. All right, last statement. Okay. X equals 5. Yes? Yes.
Is it undefined because of the open circle?
Yes, it is. Good question. Right, Adam, is it continuous at x equals 5?
No.
Correct. No, it's not continuous because. All right, Julia, you can pick. What's the word? Why is it not continuous? Yeah, it's an infinite. Or the other word sometimes is called non-removable. Okay? And it's because it's a vertical asymptote. All right. Then what is the limit as x approaches 5 from the left equal to? Hold on. There's our picture. 5 from the left. Come on. Lifeline. Infinity. Thank you. Okay. Infinity. From the left, the graph is pointing up. Okay. The limit as x approaches 5 from the right. Carrie, over here. Yes, infinity. Okay, so the left and the right are actually the same. But because of the infinity, that's why we get the infinite discontinuity. Okay, and f of 5. Zeta, f of 5 is?
Or would it just be,
It is a vertical asymptote, so there is no point there. So if there's no point, because this last piece is asking about the point on the graph, there's no point, so we say undefined. Whew, okay. I'm going to write the limit definition once at the top of the page here, and then with each of the problems, I'm not going to rewrite the definition, I'm just going to use it, okay? So in order to be continuous, okay, from the left, has to equal the limit from the right has to equal the point. Okay, left equals right equals the point. That is continuity. Okay, here's our example. This time, no picture. Okay, no picture. We're going to do it by looking at those statements algebraically. Is f of x continuous everywhere? Question mark. Okay, everywhere. That's for all x's. Here's my f of x. It's going to be a piecewise definition. Okay. And we'll do x squared minus 1 or more than 2. So I have two pieces. I have a left side, right? I have a left side. That's this first part. Okay. I have a right side, which is this part. Okay. Which is the second step of my continuity definition. And then I have a point, which could be green or orange, or it could be a third color based on the definition. All right, so we have two pieces. So I'm going to look at the left side first. Is this, right, is that graph continuous? Y equals 5 minus x. Yeah, it's a straight line. It's continuous, so yes. All right. Now I'm going to look at the right side. Is y equals x squared minus 1 a continuous graph? Yeah, it's a parabola. Okay, so now that I've established that the left side is good and the right side is good, what about the transition, right? Because it switches from green to orange at x equals 2. And so that's where you actually have to check the continuity definition, because that's where the left and the rights could be different. Okay, so I'm going to set up my statement. At x equals 2, I've got to do green. Okay, the limit as x approaches 2 from the left. Okay, 2 from the left is 5 minus x. That's where the green part comes in, right? Okay, equals the limit as x approaches 2 from the right. Okay, that's the orange part. Okay, and the point. Okay, f of 2. So now as I'm looking at this, is f of 2, you can raise your hand, going to be green or orange? Yes, Pedro?
I was just gonna say, it's in the X squared minus.
Yes, that too. Okay, thank you for the correction. And which one is f of 2? Should it be green or orange? Yeah, okay.
Green.
Green, yes. Fantastic. Okay, so this one is supposed to be green. All right, evaluate. Remember how you just summarized how to evaluate limits? Just evaluate. So we get 3. 3. Oh. They're all the same. So, yes. Is f of x continuous everywhere? Yes, because, right, the left side is continuous, the right side is continuous, and the transition is continuous. It's continuous everywhere. And it's going to be the exact same question. Yes.
Sorry, but is the left and right, are they always gonna be?
No, they don't have to be. It just happened that this example is continuous. Based on how these limit statements simplify, you could have a jump or a point, or I guess you could have a vertical asymptote in a piecewise, or it could just be a vertical asymptote.
So when you did the left and right and you have like y equals y minus x, or sometimes that could be no.
It could be. It's rare. That's sort of like a dirty way to ask that question. It is, because usually when you're looking at piecewise, you're like, oh, transition. But it's possible I give you something like 1 over x minus 3. You're like, that's a vertical asymptote. Yeah. Okay, so is f of x continuous everywhere? All right, here's our f of x. Okay, we'll just do 2 parts. X squared minus 1, and we'll do x is less than 4. Then we'll do 3x plus 1 for x is greater than or equal to 4. Okay. Same thing. The left side. The right side. The transition. Right? Those are the 3 things I need to look at. I have a left side, a right side, and a possible transition. Okay. This is a parabola graph, so yes, the left side is continuous. This is a straight line, so yes. And now I consider the transition point. Okay. The limit as x approaches 4 from the left. Right? I'm just setting it up. The limit as x approaches 4 from the right. And f of 4. There you go. That's the setup. Now you go and you pick green, orange. Okay. So we've got green. We got orange. All right, Daria, is the left side green or orange?
No,
Green. Okay, so x squared minus 1. Okay. Dane, what is the left side evaluate to for the limit? This statement here. Yeah, what do you get when you evaluate this limit statement? Yeah, okay, so 4 squared, so we get 15. Okay. Addie. Which one is the right side? Yep, 3x plus 1. Okay. Colin, what do you get when you evaluate the right side?
You get 13.
Yeah. So we get 13. Okay. 15 is not equal to 13 because when I set up the statement, it was more of like a question mark. I don't know if they're equal. Okay. So the last part. Lance, f of 4. Is this one going to be green or orange? Okay, so look at the 4, okay, which is the x value. Which one of these domains does x equals 4 fit into?
Orange.
Yeah, orange. Okay, perfect. So this one is going to be orange. So I'm going to plug in here. And so this actually gets 13. All right. So is f of x continuous everywhere? Agnia, yes or no? Is it continuous everywhere? Yeah. No. It is not continuous, right? See here at the transition point? The left and the right are not the same. So it's not continuous because, all right, vocab word. Luke. Where are you? There you are. Can you give me one of those 3 vocab words for discontinuities? Which one is this? That's right, yeah. Go back and look. It's fine. We're still learning. Okay. Which kind of discontinuity is this? So look at our limit statements. The left is 15 and the right is 13. No. Hold on. Can you, lifeline, look at anybody around you. I think Colin might have an answer. It's jump. Because of a jump. All right, guys, you've got to think about it. The left side is 15. The right side is 13. They're not in the same place, and it's a jump. Okay, so you have to look at how your statements simplify in order to get the right vocab word that goes with it. Okay, it's not continuous because there's a jump. I mean, I could say there's a jump at x equals 4, but yes. All right. Yes.
What about like the left and right? Yes.
Oh, okay. So is this continuous? Like, is the left side continuous? Right? Because I have the left, the right, and the transition. It's possible that these things aren't, but usually they are. Okay. Next question. You guys can do 3. Find K so that f of x will be continuous. All right. So I'm telling you that f of x has to be continuous. So I'm going to give you a piecewise. Usually continuity deals with piecewise because you've got more than one piece and you're trying to see if they match. All right, negative x plus 3 we'll do for x less than or equal to negative 1. And then we'll do k x minus 5 for x is more than negative 1. Okay. All right, Julia, which one of these things is the left side?
Minus x plus 3.
Yes, the top one. Okay. Yep. All right. Maya, is y equals negative x plus 3 a continuous graph? Yes. Okay. So the left side is continuous. All right. The right side. Tessa, which one is the right side? Okay. So the k is basically representing the slope, right? I just don't know what it is. Jasmine, is the graph of y equals kx minus 5 a continuous graph? Yes. Okay, because it's just a straight line. All right, now we have the transition. Okay, transition. So I've got my limit statement, right? I had it at the beginning. The left side, so the limit as x approaches negative 1 from the left. The limit as x approaches negative 1 from the right equals, right, that's my statement. The left, the right, the point. Yes. Negative 1, thank you. Negative 1. Okay. Silent, green or orange? Which one goes here?
From the left.
Mm-hmm.
From the left, that would be
Green. Okay. Yep. All right. Dylan, what do you get when you evaluate the left side? Which is this one. Yeah, so negative 1 plus 3. Oh, not 2. Four, yes. Okay. Got it. All right. Adam, which one is the right side? Yes. K. X minus 5. Carmela, what happens when you plug in negative 1 and evaluate this middle statement here? Yes. Okay. So you plug in for the x coordinate. And, right, we just have a k here, so it's negative k minus 5. That's it. Okay. All right, I'll take a hand this time. All right, f of negative 1. Green or orange, and what do you get? Okay, Zeta?
it's the green and the
Yeah, it's green, so, which is the same. All right, guys, put it together. Obviously, these two 4s are the same, so I'm just going to look at this side right here. So 4 equals, I'm going to add 5 to both sides, and I'm going to say k equals negative 9. All right. And then I'm going to give you a little visual in Desmos on what we just did here. Okay, so I'll let you write it.
It's kind of scary.
No, you can do it. Okay, here we go. All right, here we go. There is the graph. See if I can resize this a little bit. Okay, scooch over. Resize. All right. Okay, there we go. There's the green graph. Let's change its color. Let's make it green. Okay, so there's the green one. And this is only for the domain of x is less than or equal to -1. All right, notice how it kind of cut off right there at the x-coordinate of -1. Okay, so now I'm going to graph the orange one. Y equals kx minus 5. Okay, I'm going to add a slider for k. And I'm going to add the domain. So this is for x is more than -1. And let's make it orange because it's orange. Okay. And notice that these two things don't touch. But as I change the k value, I'm trying to find the k value so that it's a continuous graph. That's what you did. Okay, you found K so that the green and the orange actually meet in the same place. Could you check it in Desmos to see if you got the right value? Yes. You're looking to see where those two things overlap. All right, last question. Just going to change the format for you just a little bit. Okay. Same question, different format. Find K so that f of x will be continuous. Okay. X squared minus 3x over x squared minus 9 okay. All right. So I have two pieces here. Okay, I've got green and I have orange. And my continuity, oh sorry, I have the left and the right, and I have the top piece and the bottom piece here. Okay. I'm gonna come back and we're gonna look at the left side and the right side after we do a little bit of work here. Okay, and I'm gonna look at this value first. You can do these things in any order. I'm not sure what to think about comparing the left side and the right side for being continuous. So I'm not gonna start there. I'm gonna start here at my limit statement. Okay, so I need the limit as x approaches 3 from the left. And I need the limit as x approaches 3 from the right. And I need f of 3. Those are the three parts of my continuity definition. All right. Green or orange? That's what I need to know. Ian, is 3 from the left green or orange? Why do you say orange? Okay, that's right, Lifeline. Look around you. Okay, let's say this. It's green, but I need to know why. It's green. But why? Who can tell me why? Yeah? Yeah, you're not at 3, you're just approaching 3. This is not equal to 3, so that is everywhere else. It is the left and the right of 3. So that is the left and the right. Okay, so as I do this, okay, can I factor this, please? Because it's like begging to be factored. It is. It is.
Is that what goes on with these things like that?
Yes, it is. I'm like trying not to skip too many steps. Okay. So this is the same. Okay, yes. Do you see how the left and the right are the same? So I'm just gonna do it once. Okay. After I factor and reduce, what do I do to evaluate the limit? Come on, I got awesome flowcharts. What do I do now? Hands? Anyone? Anyone? Yeah? Just plug it in. Just plug it in. So I get 3 over 6. So I get 1/2. Fancy that? Okay. So these two pieces were green. Okay. Because that is the left and the right. Okay, the point. F of 3 is orange. Is orange. What do you get when you plug in 3? So over here, now that I've sort of investigated, the left and the right were this one right here. Okay? The left and the right were that piece. Okay? The point is actually, okay, I guess the middle, is this one right here, which means that the y value is k. So what is k supposed to equal? 1/2. Because that's what happened when I evaluated those limit statements. All right. Okay. So somebody asked me, what happens when these two things, are these always continuous? Not necessarily. No. This one has a hole because of the common factor you reduced. So it is possible that some of these pieces aren't continuous. Okay. That is it.